When we're talking about derivatives, we've talked about this a lot already. The derivative is the instantaneous rate of change of the dependent variable, which is not always y, but if it's just a really generic scenario, it's y, right? With respect to its independent variable. Which, again, is not always the x, but in a very generic scenario is probably going to be the x. Okay, so it's the rate of change of the dependent variable with respect to independent variable. A few things to help you remember, like what that's talking about, is that a derivative is a rate of change, which is like a slope, right? Which is your change in y over your change in x. Or whenever we're talking about taking a derivative, one way we represent a derivative a lot of times is we call it dy dx, right? The derivative of y with respect to x. So both of those things sort of lend themselves to what we're talking about here. It's the rate of change in y with respect to what's happening with the x. So one thing that's going to be really important in what we're talking about here is our units. Because you almost for sure are going to probably have, I'm going to say, 2 full free response questions that are in context of a problem, or of like a real world problem. Sometimes it might be 3, but usually there's at least 2 that are not just naked problems. They're not just math problems. There are so many fish in a lake, and the rate of change of fish is this, or it's within context. So it's really important in those sort of cases that we include our units for that. So when we're talking about the units for a derivative, the unit for f prime is going to be the unit for f divided by the unit for x. Or you could think the y-axis divided by the units for the x-axis. Here, change in y over change in x. In this case. So, some of the questions that we're going to have are going to look like this. They are just going to ask us about the units themselves. Now, in a free response question, they won't ask you about units only, but there are a lot of questions out there where units are a point. If your units are wrong, you lose that answer point, or you lose that point. So, it's really important for us to pay attention to. So, we've got the function c of t gives the cost in dollars of running a piece of equipment for t hours. Now, I, on purpose here, have not used x and y because it makes it a little bit easier when it's the typical x and y. But in this case, what is our independent variable? Like typically it's x, but it's not here. What's the independent variable here? It's t. So whenever we're thinking about, like in this case, change in y over change in x, it's not actually x and y for this problem, right? It is change in c, or you could call it f, either one here, because they said c equals f of t, either one, over our change in t. So if we're thinking about units, we need the units for c divided by the units for t. So what were the units for c? Dollars, right? So we got dollars, and then what are our units for t? Hours. So that is dollars per hour is another way you could say it, or you could say dollars per hour. They'll accept multiple types of notation there, but dollars per hour is what we're looking at. And if you think about what the graph of this function looked like, who knows what it looks like, but hours was on the horizontal axis and dollars was on the vertical axis, right? Now we got to think about units for f double prime. Okay, so if we're thinking about f double prime, we're thinking about changing y over changing x, but this time, because we're looking at f double prime here, y isn't really y, and it's not c this time either, right? When we're talking about the second derivative, we're talking about the rate of change of the first derivative, right? So the x-axis would stay the same. It'd still be hours. But our y-axis here would be the question before, right? It would be dollars per hour. So we're talking about not the change in C, but the change in C prime or F prime, right, whichever one you want to call it there, over the change in T. So for our first derivative, our units were dollars per hour, and now our T is hours. So several ways you can write this. You could do, I just like to do this, dollars per hour per hour. Another way you can write it, it's a little more condensed, it looks a little prettier, but what I find is kids do it wrong too often, so I don't do it as much, is like if I think of this, this is dollars per hour divided by hours, right? So I could make this bottom one a fraction by putting it over 1. Dividing fractions is easy as pie. I could flip the second and multiply. So I've got dollars over hours times 1 over hours. And then that is going to be dollars per hour squared. So dollars per hour is the same as dollars per hour squared. What I find, students wouldn't do it so much on this problem because you don't usually talk about square dollars, right? Like you would never have square dollars. But a lot of times you're dealing with feet, inches, miles, meters, and you would have square feet, square miles, square inches, square meters. And kids put the square on the wrong term. They'll do like feet squared per hour when it should not. It should be feet per hour squared. So that's one reason I kind of just say leave it dollars per hour per hour. But it's good to understand that those are the same there. Okay, so let's look at the next one. Okay, the time t it takes to run a distance d is given by the equation t equals capital R of d, where t is measured in hours and d is measured in miles. This one you got to be really careful on, because when I see t is measured in hours and d is measured in miles, I automatically think the answer is miles per hour. But it is not for this one. It is going to be in most cases, because t is usually your independent variable. Is t your independent variable here? It is not. What is our independent variable? D, which is the distance, right? So our change in y over our change in x is really change in d over our change in t. Oh, I'm sorry. I still did it backwards. Gosh. Change in t over change in d. If time is involved, it's almost always your independent variable, but it's not here. In this case, T is measured in hours, and D is measured in miles. So hours per mile. That sounds weird because we don't use that very often. Even though if you really think about it, we wouldn't do hours per mile very often. But like if I say, Mason, what is your mile time? What is your mile time? It's something ridiculous, isn't it? Good gosh. Ella, what's your mile time? 18 per girl. Oh my gracious. That's insane. Oh, mine would be double digits for sure. For sure. Actually, Hunter over the summer was supposed to run a mile for PE. Hunter ran his mile in like over 10 minutes, which is ridiculous. He should have done a lot faster than that. He also used fishing as his physical activity for the day most days. And Coach Foster counted it. But I was at the park walking during Henry's swim, and I was like, I think I could run a 10-minute mile. So I was going to try, and I ran for about a minute and a half and decided that I was going to die before I got to the end of the mile and quit. So I maybe can't run a 10-minute mile, but I was wanting to prove to him that he needed to speed it up if I could do it, but I don't think I can. So let me get back in shape a little bit. But anyway, in that case, we're doing minutes per mile, right? So this is odd to do hours per mile because usually if we're talking about people running, right, maybe we're talking about a turtle that is going to take a lot longer there. So hours per mile seems a little bit odd, but we do maybe talk about this sometimes, right? So we're looking at hours per mile. So if we're going our double prime, right, we're doing our change in our y over our change in our x, but in this particular case, we're talking about our change in like the t prime or the r prime over change in the d right here. So change in t prime is the answer to part A, right? That is hours per mile. And then we would divide it by miles again. So you could say hours per mile, or you could say hours per mile squared. And so you can keep going with this. It just usually runs out of things that start to make sense, right? You could, if you took a third derivative, it'd be hours per mile, or hours per mile cubed, right? You just basically keep dividing by whatever your independent variable is every time for that. So knowing the units can really help you keep that straight for the problems here. And they're really important to include. If they give you units for the problem, you need to include them in the answer. They're not always a point on the answer, but a lot of times they are, and it would be silly to lose that point. In fact, they could give you a question you don't know how to do at all. And if you can come up with something, maybe you can't just write down a 7, but you could do something crazy to get 7, right? Like, I know this is wrong, but I'm doing this and I got 7. And then you put hours per mile squared on that end of that answer, you'll get the unit point even though your work for the actual problem was way off there. So a lot of times these can be easy points, but they're also easy to leave out and forget. Okay, so let's talk about, here we're not going to do a ton of math in this section. What we're worried about is explaining our answer. What does this mean in context of the problem? So, in this case, the length of a scarf is given by the function capital L equals S of t, where length, capital L, is measured in centimeters and time, t, is measured in minutes. What is the meaning of S prime of 7? So we don't know the equation. We're not finding S prime of 7. We're telling what it means. So I would start off with units on this because sometimes just knowing the units helps you form your answer, right? So, like, you don't have to write this every time, but I will right now because I'm explaining it to you. Changing y over changing x, but in this case, y is not y, right? Our dependent variable in this case is our L, and our independent variable is the T. You also could call that S, like when they give this to you in this form, L or S could be considered the independent variable, dependent variable there. So changing L is length. Length is measured in centimeters. And then T is time. It's measured in minutes. Okay? So, if we're talking about a first derivative, it is a rate of change of the dependent variable that you're talking about, right? So, we're looking at centimeters per minute. If they give us a number right here instead of x. So if they said, what does S prime of x mean? We would not have to do this, but they said S prime of 7. So 7 is getting plugged in here for T. T is time. Specifically, time in minutes, right? So we would want to start off with at, you don't have to say T equals, but I like to. T equals 7 minutes or at 7 minutes. What you want to avoid right here, don't say things like over the first 7 minutes or during the first 7 minutes, because that doesn't mean at 7. That's talking about all the way from 0 to 7, right? We're just talking about at 7, at that moment in time. This is our instantaneous rate of change. So at T equals 7 minutes, we're talking about the length of the scarf, right? So the length is, now, in this particular case, we don't know what S prime of 7 is. We don't know if it's positive. We don't know if it's negative. We don't know if it's a big number. We don't know if it's a small number. So instead of saying increasing or decreasing, I'm going to just say changing. If I knew the answer, if I knew if it was positive or negative, I could say increasing or decreasing. But I don't know what it is. Maybe the person's messed up and they're pulling it out, right? So it could be decreasing. So the length of the scarf is changing at a rate of S prime of 7 centimeters per minute. Now, more than likely, if we had a number, it's probably increasing, right? I'm assuming we're knitting the scarf and not pulling it out, but it could be the other way. Okay, if it's a first derivative, it's going to be the rate of change of whatever your dependent variable was. Okay. All right, let's keep going. This one is calculator active. It is, in fact, going to require us to do a little bit of work. You don't necessarily have to get out your computer for this. It's pretty basic, does most work. I think I even tried to do, let's see if I did this for this one. I made myself a Desmos where it's already typed in here. Why are those showing up? I told it not to show up. Okay. So we are looking at this equation gives the height of water in a swimming pool at time t. The height h is measured in the height h is measured in feet, and the time t is measured in hours since midnight. I should have made this a little bit better problem because this is fluctuating in a wild manner. because our swimming pool has gone from 0.85 feet deep to 4 feet deep in like 4 hours. So it's like empty, then you're filling it up, then you're draining it back again. Should probably make that number, should have made this number right here a little bit smaller so it would make sense. Certainly you might see a pool sort of, you know, if you fill it up every night or something, put a little extra water, you're going to see it like go up and down, up and down. But this is a ridiculous problem. Here. The height is measured in feet, and time is measured in hours since midnight. Find the instantaneous rate of change of the height of the water in the pool at 10 a.m. Okay, so this question, what is it asking us to find? Yes, derivative at 10 a.m., right? So, and what this is telling us here, instantaneous rate of change of height, right? That is what is telling you that you are looking for h prime. And then, of course, they tell you a specific time. So that tells you h prime of 10. Now, here's the beautiful thing about if this is a calculator active problem. They will ask you questions like this sometimes. And if they give you something like this, here's all you have to do in Desmos. H prime of 10. That's it. Let me make sure I am in radian mode. Yep. H prime of 10. All right. So if this was a calculator active question on a free response question, all you have to write is H prime of 10. You do not have to plug anything in. Finding the derivative, you don't have to do any of that because it's calculator active and they expect you to do it on the calculator. So h prime of 10 equals 0.64, we'll round that to a 3 right there. You could keep more decimals if you want. 0.643, and then I want to put units with it because this is certainly a problem that has units. Connor, what would our units be for this one? I think it's okay to just say feet per hour here. So this is kind of the opposite of what we were doing in 3. We're not having to explain it. We're having to read it and understand that that's what it's asking us for, right? And you will see problems that ask you to do both. Like sometimes they'll say, find, f prime of 7 and explain what it means in context of the problem. Other times, they will give you a question that says, at time t equals 7, what is the rate of change of the blah, 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 and you have to know it's asking for that. So we'll see both of those things.
So the meaning is different than what we said.
It's different because of the context of the problem. So like here we're looking at feet per hour. So in this case, the height of the water in the pool is changing at a rate of 0.643 feet per hour. Since we know the number, it's increasing here because it's a positive number. Whereas like on the last problem, we were talking about a scarf. So it's still the rate of change. I didn't use the word instantaneous, but I could have, right? So if I said at 7 minutes, the length of the scarf is changing at an instantaneous rate of s prime of 7, that would be okay. By saying at t equals 7, you are implying that it's instantaneous right there. So it's the same thing, but due to the context and the wording, it's a little bit different. They may not always put that word instantaneous right there. But if you do see it, you know for sure you're talking about the derivative at that single point. What you have to watch out for is sometimes instead of saying instantaneous, they'll say average rate of change. If they say average rate of change, they have to be talking about over an interval, not at a specific time. There. All right, so here is our next calculator active problem that I have also put in here. But its way up here. It's okay that we see it. So for this equation, we've got S of x equals this crazy stuff. It gives the weight of sand in a storage container after X days, where weight is measured in tons. Okay? And so this is going to be one that asks us to find these values and then explain the meaning. Finding the values should be super duper easy, even though, hold on, I picked the wrong one. That's not it. Here it is. Zoom out even more. I'm gonna restrict this from 0 to 50. So 0 less than or equal to x less than or equal to 50. So we're only looking at the important part of the graph right there. So if you see a problem like this, and you might, the work is, there's almost no work, right? Like it says find S prime of 15. I'm going to type in S prime of 15. There it is, right? It's doing the work for you. Yes, we could find the derivative of this by hand. We could plug in 15 by hand, but you don't have to because it's calculator active. So, so for something like this, I would say, I like to do this. I like to say S prime of 15 equals, I like to state it alone and then talk about it, just so it's there in both places, because sometimes you can word it in such a confusing way they may not even give you credit for getting the right number. So if you do this, it kind of takes care of that, because usually you're going to get a point for the number and a point for the explanation. So 0.527. And I'm going to go ahead and think about units here. So this is change in S over change in X, because X is our dependent variable. S is the weight of the sand in tons, and X is days. So it's tons per day. So, we're talking about derivative. That is a rate of change, right? Now, notice I've got a negative derivative here, right? Like the value is negative 5.527. What does that tell me about what the function is doing? If my derivative is negative, the function is decreasing there. So, for this, we would say if or at t equals 15 days, the weight of the sand is decreasing at a rate of, now here's where you gotta be careful. You have already used the word decreasing. Decreasing takes care of the negative, right? So you're not going to use the negative number here. You're going to say 5.527 tons per day. If you say that the weight of the sand is decreasing at negative 5.527 tons per day, that is wrong. What you have there is like a double negative. Like you say that whenever you tell somebody that they're not wrong, you mean that they are actually right. So if you say they're decreasing at a negative rate, that would actually be increasing. Mm-hmm.
Can you say changing at a rate of negative?
You can. I think it's much more clear to say decreasing at the positive rate. you can get by with changing at the negative rate. So you can say the weight of the sand is changing at a rate of negative 5.527. That is acceptable. I don't think it's the clearest, so like if you were writing a paper about this for work or something later on in your life, I don't think it'd be the best way to say it, but you can get by with it. There. But be very careful, don't say decreasing and then use a negative number. Okay? Part B here, we are going to just go back over to Desmos real quick. We're going to see what S double prime of 15 is. Does it for you. You don't have to take a derivative. You just type it in. We got 0.276. So S prime double prime of 15 is 0.276. And what would the units be for this one? Tons per day squared or tons per day per day? I think these are so hard to explain what's happening here, especially in this scenario, because we're starting to get like a little bit more abstract on what's happening, right? Like I can, right on the 15th day, this is how fast the sand's going out of the whatever storage container that we're looking at, right? That kind of makes sense. So now we're talking about at the 15th day, we still want to say at T equals 15 days. We're still talking about the weight of the sand, right? Well, sort of. But this is the second derivative, right? We're talking about the change in S prime over the change in our X, right? So S prime is our rate of change of the amount of sand, or the weight of the sand. So when we're talking about second derivative, it is a rate of a rate. So if you kind of like make sure that you say the word rate twice, that really increases the chances that you get this answer right. So we're not talking about the weight of the sand is increasing at a rate. We're talking about at T equals 15 days, the rate of change of the weight of the sand is, in this case, we've got a positive number, so I'm going to use the word increasing. At a rate of 0.276 tons per day squared or tons per day per day. I'm going to do it both ways so you just see. You don't have to, just so you see. Either way is fine. Right there. So in this case, we're not talking about the weight of the sand, which is just S. Like up here, it was S, right? We were looking for that S, so we said the weight of the sand, right? But down here, we're looking for S prime, so we're not talking about the weight of the sand changing. We're talking about the rate of change of the weight of sand is increasing at a rate of. You want to see that you got, if you're talking second derivative, you want rate to be there twice. You're talking about the rate of the rate. I think those are a little harder to think about what's happening. I think one way, will be a little bit easier to think about what's happening when we talk about it in context of speed tomorrow. When we're talking about position, velocity, and acceleration. Because if you think about like a car that is accelerating, it, is going 5 miles per hour, then it goes 10 miles per hour, then it goes 15 miles per hour. So the speed is the rate of change, which is your speed, is increasing at a rate of 5 miles per hour Your speed is going up 5 miles per hour every hour, or probably not hours, but seconds or whatever. For that. All right, here's one with a table. And this one I have pulled like some stuff that you'll see from like free response sort of questions. Here, the depth of water in a rain gauge is given by the twice differentiable function r for 0 to 25, where r is measured in inches and time is measured in hours. Values of r prime, the derivative of r, at selected values of time are shown on the table above. I should say below. I moved some stuff around. It is known that the graph of r is concave down from 0 to 5. That might be a mistake right there too. I don't think so. I put it in the calculator so we can kind of look at like what's happening here. I'll let you know about that for sure when we run into how bad it gets. But so it says, is there a time from 0 to 24 at which the depth of the water in the rain gauge is changing at a rate of 0.5 inches per hour? Justify your answer. Okay, so first of all, whenever it talks about the depth of the water in the rain gauge changing at a rate, what would that be in terms of the function r? Are we talking about r, r prime, r double prime? R prime. So it's asking us, does r prime of t equal 0.5? That's what the question's saying, right? Because the is there a time where the depth of water in the rain gauge is changing at a rate? So we're talking about the rate, so we're talking about r prime, right? So looking at my table there, is r prime ever going to have to equal 0.5? Okay, I'm seeing Connor nod his head yes. Why do you say yes, Connor? Intermediate value theorem. There's a lot of, you have to use this point right here because that's the only time that your derivative is greater than 0.5. You could really use any of the other points on the graph, on the table as well, because all of the rest of them are below 0.5, but we definitely go from a lower number to a number higher than 0.5. But now what has to be true for intermediate value theorem to apply? We can't just throw it out there. We have to have a continuous function. Is r prime continuous? Very good. We know that r is twice differentiable, which means if r was just differentiable, it would not necessarily mean that r prime was continuous. But r is twice differentiable, which means we can take the derivative of this function twice. So that would mean that r is differentiable and r prime is differentiable, right? So, we are going to say since r is twice differentiable, r prime of t is continuous. You could throw in there like, since r is twice differentiable, r prime is differentiable, which means r prime is also continuous. You could, that would be correct. I don't think you have to say that. You can just make the jump from twice differentiable to r prime is continuous. And now it does not matter which point you pick here for the lower end. You could use literally any of the points on this graph except for r prime of 15. So I'm just going to pick these 2 points because here is where I see us go from r prime equals 0 to r prime equals 0.55. So I'm going to say r prime of 12, which equals 0, is less than. We are trying to prove that this is 0.5. And then we got 0.55, which is equal to r prime of 15. You could also do that separately instead of doing it in one big statement. You could say r prime of 12 equals 0, r prime of 15 equals 0.55, and then say that 0 is less than 0.5, less than 0.55. Therefore, by the intermediate value theorem, and then restate what the question asks. There is a time for 0 less than or equal to t less than or equal to 24 at which the depth of water in the rain gauge is changing at a rate of 0.5 inches per hour. So that's intermediate value theorem. That's from a long time ago. Almost anything can fit in this section, though, because the idea is that you have to recognize depth of water in the rain gauge is changing at a rate of means r prime of t, right? So we can take anything we've learned so far, and if we throw it in context of an actual situation, then it fits in this section right here. Mm-hmm. Yes, 15 to 18 would be fine. You could even do from like 0 to 15. You have to use 15 because it is the only time that r prime of t is greater than 0.5. But you could use all of the rest of the points instead of using r prime of 12. All right. Okay, it next asks us to use the data in the table to approximate r double prime of 16.5. Show the computations that lead to your answer. Using correct units, explain the meaning of r double prime in context of the problem. So they're not asking us to find r double prime of 16.5. They're asking us to approximate r double prime of 16.5. What are we going to need to do here? Slope formula, because between 18 and 15, 16.5 would be right between it, right? To estimate a derivative, we can just find the slope between the two closest points, right? And we are finding the second derivative, which is the derivative of r prime, which is what we have in the table. So we're going to be using 15, 0.55, that's 1 point. And then we'll also be using, oh gracious, we'll also be using 18, and what is 18 there, 0.4. So we'll say R double prime of 16.5. It is best to use a squiggly equal sign here because this is an approximation. And then just do slope formula. So 0.4 minus 0.55 over 18 minus 15, which is going to give us negative 0.15 over 3. And I think this would be calculator inactive. You don't necessarily have to divide that, but it does make it easier to like make the statement later if you just have a number. So that's going to be negative 0.05 there. In 4 units, we're talking about second derivative. So it's R prime divided by the independent variable, which in this particular case is our time. Another thing, you're finding the slope. R prime is in inches per hour, right? So like up here, this was inches per hour. And then 18 minus 15, that was hours. So we're looking at inches per hour per hour. Okay, so we want to explain this, and it is a rate of a rate, right? So we're going to say at t equals 16.5 hours. We're not talking about the amount, oh gosh, I've already forgotten what we're even looking at here. The depth of the water in the rain gauge. We're talking about the rate of change of the depth of the water in the rain gauge. So the rate of change of the depth of the water is our rate of change of the depth of the water increasing or decreasing? Decreasing? How do we know, Connor?
It's negative.
Okay, yeah, I mean,
Okay,
yes.
R
You hesitated on saying it, but I understand what you mean.
0.05 inches per hour is negative.
Correct.
Okay.
There. So we're going to say the water is decreasing. Since he did ask permission, I'm pretty sure I was going to let him get off the hook there, but it was a close one. He knew what he was doing, at least. It's like if you ever, like, every once in a while, like, Henry will want to say a cuss word. Mom, can I just say it? Mom, I'm going to tell you what somebody said. Can I just say it? Go ahead, Henry. Tell me what he said. So, Connor asked permission before he said that. Said the I word. At 16.5 hours, the rate of change of the depth of water is decreasing at a rate of 0.05 inches per hour. When you're talking about the second derivative, you want to make sure that you've said rate twice. If you've said rate twice, doesn't guarantee it's correct, but it helps ensure that it's going to be correct. Okay, questions? All right. I want you guys to have some time. That last one's just more of the same. So, I mean, you're not going to have a ton of time.